Today's class is on computer architectures, and this is an important topic because all computers, basically, you can even think of your smartphones, so no matter their size, they all still are based on some set of rules that define how the software and the hardware work together and how they interact so that they can accomplish certain goals. And this is what these rules basically and this composition define the computer architecture. So basically it is about the organization of the components that make up the computer system and also the meaning of the operations that guide the functions. So we are going to go more in depth on the traditional computer architecture, which is actually a standard one, and it has been developed a long time ago, and it's still what most of the computers are based on today. So the traditional and well-known von Neumann architecture was first published basically by John von Neumann in 1945. And this is based basically on the stored program computer concept, where both the instruction data and program data are stored in the same memory. And this is the design that is still in use by most of the computers that are produced today. It's also known as the classical concept of a universal computer. So you can see here, this is the basic concept of this von Neumann architecture, where it consists of 5 basic parts, where one big part, 2 of them are basically in one, which is known as the central processing unit. So the green box that you see stands for the central processing unit, or CPU, or it is also known as a microprocessor or just processor. And it is the electronic circuit. In general, this is an electronic circuit that is responsible for executing the instructions of a computer program. It contains basically the control unit, so Steuerwerk is the control unit, and Rechenwerk is also known as arithmetic logic unit. Here I have the translations. So it consists of these 2 parts, and it also has some registers that enable the operations, basically. So in addition to the CPU, the von Neumann architecture contains also input device or input unit, and then it has an output device or output unit, and it has a memory unit. And there are different kinds of flows or connections, basically, or interactions between the different units. So you can see here from the control unit, the red arrows denote the control flow. So the control unit basically controls the output device, the input device, the memory unit, and the arithmetic logic unit. And you can see with the black arrows, we can see the data flows. So we have from the input unit to the ALU, or the arithmetic logic unit, data, and then we have data flow from the input to the memory, and then we have bidirectional data flow between the arithmetic logic unit and the memory unit, and then also from the memory to the output. And of course, this is like for inputting and for outputting data. So the main functions are very intuitive. So the memory unit, of course, it is for storage of programs and data. And the arithmetic logic unit is about executing arithmetic and logic operations. Then the control unit is about the control of the execution of programs. And then the input and output is for input and output of programs and data in and from the memory. So in general, the basic concept of the von Neumann computer is that the structure basically is independent of the problem that it needs to solve. And then for every problem, the processing instructions are basically entered from the outside and stored in memory. As I mentioned already previously, one of the basic concepts and the basic principles is that data and instructions or programs are kept in a single storage, and then instructions should be encoded so as to be modifiable by other instructions. And this meant that one program could also be treated as data by another program. So in general, because the programs and data are in the same memory, they are also divided into units of equal sizes. And basically we have registers and we have memory cells or memory partitions. And they are all numbered. And these numbers are called basically addresses. So with these addresses, it's like you can imagine in a street, you have a number of your house. So it is an address also. In a very similar way, here the memory cells have addresses that allow a direct access to these memory cells. And then the successive commands are always stored in a successive memory cells in a program. So when you execute a program, you execute it sequentially. Except, so basically you always, when you want to address the next command or access the next command, then you just increase the command address by 1. And of course we have exceptions whenever we have jumps in programs. So you can have an unconditional jumps like the go-to commands, which just basically can jump into any address, into a command at any address. Or you can have conditional jumps, which basically go to a command at another address if a certain condition is fulfilled. Otherwise, also as what is typical for computers, both programs and data are binary encoded. So as I already noted, the von Neumann principle or architecture is still in use today. So modern computer architectures or computers are still based on this architecture in general. Of course, there are some modifications. So still the functional units of a nowadays von Neumann computer are the following. So we have the random access memory, we have the CPU, which contains the ALU, so the arithmetic logic unit, and the control unit. Then we have input and output units or devices. And then we have the internal data pathways or buses, which are used for the information exchange between the different units. We'll talk about buses in a little while, but in general, there are 3 kinds of buses. There is an address bus, data bus, and control bus. And these buses are links between the components or devices that are connected to a computer, and they usually carry data. So they also have very strict schedules. So they pick up data or they drop it off at a regular interval. And just for example, if you have a bus that, so they also have frequencies. If a bus operates at a frequency of 100 megahertz, it means it completes 100 million data transfers per second. And this is also known as a bus width. So this is in general, but also this in general, We also have in these new computers, we have memory hierarchies or hierarchy of memories, which we will also discuss in the following slides. You have some different levels of memories that have different capabilities. Then we also can have different or more arithmetic logic units. And then we also have communication over a central bus. So we will see this in the following slides in more detail. So now we will go into more detail of all the elements that are in the von Neumann architecture, and we start with the random access memory, also known as a main memory or primary memory. So it has the logical structure of this main memory is that it has a sequence of equally sized enumerated memory elements, and each of them has an addresses so that they can be directly accessed. And every memory element consists of a fixed number k of binary places or bits. The typical sizes for typical numbers for k are 8, 16, 32, or 64. So then we also have different, when we talk about a memory element of size 8 bits, then we call this a byte. Or we can also use word, and word can have different meanings. And it is also used as a synonym for a memory element. And it can, in general, it refers to the composition of 2, 4, or 8 consecutive bytes, whereas the last one is also known as a double word. So furthermore, the number of a memory element is also known as the address of this memory element. And these memory elements are basically the smallest addressable units. So you cannot access, let's say, the second half of a memory element. You have to access the whole memory element. And every memory element has a unique address. And here we have to differentiate between virtual or logical and real or physical addresses. So the virtual or the logical address is used as a reference to address basically the physical address. And the logical address is a virtual address, also known, that's why it's also known as virtual. And usually the program needs physical memory for its execution. However, the user never deals with physical addresses. You don't work with them in general. But when you program, the program generates logical or virtual addresses, and these are then mapped to physical addresses through the memory management unit. So you don't really deal with this very much, but this is the one that exists in the memory, and this is how they are numbered. So the addresses basically of successive storage items, they always differ by 1. So they are consecutive. And you can also access a memory element directly if you want, optionally, basically through the address. So, and here is one example where you can see if this is the main memory or the random access memory. Here we can see the addresses 513, 514, 515, and in each address here you can see we have 16 bits, and we have three numbers that are represented in these consecutive memory cells, basically, or memory elements. So we have 28, 6, and 33. So as I already mentioned, the modern computers actually usually have hierarchically organized sequence of memories. And the goal of this is to minimize the storage access times. So they don't have just one memory, but they have a couple of different memories at different levels. And here we have the hierarchy. This is a typical hierarchy, but there can be more caches, more cache memories, etc. So the CPU in general basically has registers that are directly assigned to the CPU, and it needs those registers for performing the operations. Then the next level is a cache memory, which is a very fast and usually limited in size memory, which is basically in the between the CPU and the main memory. So when the CPU works, it first checks whether it can find something in the cache, and the cache can use different algorithms basically and try to predict which items would be accessed next, let's say, based on different algorithms, and keep those in the cache. So usually, if it has good algorithms, it can have a very good rate. I mean, it can go even up to 95-99% that whatever the CPU needs, it can find in the cache. And then if it cannot find whatever it needs in the cache, then it accesses the main memory. So it really also depends on how good the algorithms are for trying to guess what could be the next command or the next data that the CPU might need. So it is important that if there is a poor utilization of the cache, it can really slow down computers considerably, and that's by a factor of 10 and even more. So the main memory then, it consists of two parts, and one is the read-only memory, which stores system functions that are usually required for booting the system when you restart it. And then the random access memory, which contains data and the user programs. But sometimes when you talk about this main memory, usually people forget about the read-only memory, and they talk mainly about the random access memory. And so that's why sometimes when you say the main memory, it is sometimes used as a synonym for the random access memory. Here you can see also, it's a very nice presentation of how these differ, the memories. So you can see the price per bit. It is for the registers, it's much higher than it is for the main memory. So that's why the main memory is bigger than the cache, and then the cache is bigger than the register memory. This is the access time, so you can see it's much faster to access the registers and then the cache, and then it is slower to access the main memory. And then this also corresponds, so the price also corresponds, as I already mentioned, with the capacity. So usually the main memory is larger, and then it decreases basically as you go further up here. So the registers have the smallest capacity. So the arithmetic logic unit, as its name says, is about the processing of data. So its main task is processing of data, and it serves to perform different arithmetic and logical operations, to do comparisons and logical decisions, and that's why it also contains registers and functional units. So the registers basically serve for storage of operands, of the results of an operation, or the state, basically the state descriptions of the different functional units. So the first two are known as accumulator registers, and then we have status registers. So you can see here an illustration. So here we see two registers for operands, and this is the arithmetic logic unit that performs an operation and then has a register to store the result. And then we have here the status register, which in general is a collection of bits that record various aspects of the results of previous calculations. So anything that needs to be remembered or the status of the arithmetic logic unit could be stored in this status register. So the functional units or the arithmetic logic unit, they basically link those operands that are stored in the registers. And then we have typical operations for this unit. Could be a transfer operation, so like loading or saving of data. Boolean operations, so the AND, OR, as we've seen it before. Then arithmetic operations, so addition, subtraction, multiplication, and division, or shift operations, so left or right shifts of registers. The control unit of the computer basically is there to tell the arithmetic logic unit what operation to perform on the data that is being input, and it also stores the result in an output register. So then the control unit also moves the data between these registers, the arithmetic logic unit and the memory. So in general, the type and the sequence of the arithmetic operations to be performed are defined by the control unit, and also vice versa, the control unit receives information about the status of the arithmetic logic unit. So these are the bidirectional signals that are control signals that enable the control of the control unit over the CPU, over the arithmetic logic unit actually, because the control unit is part of the CPU. So the main task of the control unit is basically the execution of the operations that are specified in a given program. And for this reason, it also contains two additional components, basically the instruction register, which contains the instructions that are, or commands that are currently being executed. And then we have a program counter that contains the address of the current command or instruction in the memory. So the main tasks of the control unit is basically the following. So before I go into detail, I just would like to say that the CPU in general in this von Neumann architecture works basically following a process that is known as fetch, decode, and execute. And these are all controlled through the control unit. So basically, fetching the instruction means that the next instruction is fetched from the memory address that is currently stored in the program counter and stored in the instruction register. And then at the end of the fetch operation, the program counter basically points to the next instruction that will be at the next cycle. Then we have the decode cycle, or the decode step, in which the control unit basically interprets the instruction, and during this cycle, the instruction inside the instruction register gets decoded. And then we have the execution, where the control unit of the CPU basically passes this decoded information that has been decoded in this step before, and this is passed basically as a sequence of control signals to the relevant function units of the CPU to perform the actions that are required by the instruction. For example, reading values from registers or passing them to the arithmetic logic unit, or maybe to perform different operations, maybe arithmetic operation or shifting, and then writing these results back to a register. So if the arithmetic logic unit is involved, then it sends a condition signal back to the control unit. And here we see an example of this fetch, decode, execute cycle. And we are going to basically control the sequence when executing an adding command, basically, which is increase the content of the memory cell 500 by 16. And this is the initial state. So the contents of the program counter is 1000. So this is where, this is the command. Where is this stored? Here. The content of the memory cell 1000 is basically the command. So basically this command. And then the content of the memory cell 500 is 17. And now we go through the cycle. So first we fetch. So basically we get the command, which is we go to the cell, memory cell 1000, and we fetch the command basically in the instruction register. So you can see here, this is the program counter, this is the instruction register. And then the second step is to decode. So basically we recognize in this step, we recognize that we are dealing with an addition of the content of memory cell 500 with the constant 16. And the memory cell 500 contains the number 17. So then in the third step, the execution, we fetch the operands and we execute the command. So we fetch the contents of memory cell 500, which is 17. Then we execute the addition, 17 plus 16. We write the result after the memory cell 500. And we increase the program counter by 1, basically, to the next value. So this is an example of how a whole fetch, decode, execute cycle works, and how, in general, CPU operates. Input and output devices are something that we are all very familiar with. They're basically the external input and output of data. They're used for external input and output of data and programs. And input devices are those with which we feed data into the computer, and output are where we can store data. So as input, we can consider a keyboard, mouse, all the different sensors, and as output, we have the display, printers, speakers, and we can have also devices that can both input and output data or programs, such as other computers over modem or DSL or internet or Ethernet or etc., or hard drives or flash memories, so like USB sticks, CD, DVD, cassettes, etc. What is important with all these devices is that we have to be always careful in the sequences of the data. So the data, how they are being processed, it's always different. The format of the data can be different from one device to another, and the speed of the data transmission can differ between different input and output devices. As we already noted before, the concept of a bus is very important in this architecture. In general, just physically, the bus is a collection of wires, basically chips and slots inside the computer that we use to transmit data from one part of the computer to another part. Let me just turn on the pointer. To another, basically from, and also from peripheral devices. So it is also called a pathway in the computer that is used for traveling of data, you can say. I mean, that's why that corresponds to the name bus. So in general, the functions of the bus are that it carries information from one component, you can see here, to another. So this is the bus. And it carries data, address, or control signals. And that's why we have data, control, and address buses as well. And this is how the different components interact with each other. So as you can see here, it has either transmission or signal lines, or it can be data collection routes. So the bandwidth of a bus, so it can have different bandwidths or different speeds, and it is determined by the number of parallelly transmissible bits, or basically is the number of lines or wires that it contains. So the data bus, we said there are these three different types of buses. So there is data bus. There are also other types, but these are the main ones. So the data bus, the address bus, and the control bus. As their names say, so the data bus is responsible for transmission of data in a bidirectional way. And then the width of the data bus basically corresponds to the number of bits of the memory element that is linked to it. Then we have the address bus, which is about transmission of memory addresses that are calculated by the CPU. And then the address bus and the data bus are always used together. So the addresses that are in the address bus always indicate the sources or the destination of the transmission of the data on the data bus. So they complement each other, you can say. And then we have the control bus, which is about transmission of control signals between the CPU and the different other functional units. So here you can see an illustration. Here we have the data bus. Here we have the address bus, which are always used together, as we said. And here we have a control bus used for transmission of control signals. So the bus in general is a limited resource. So it means it cannot be used by everybody at the same time, but it can be used by one unit at a time. So the allocation of this limited resource is very critical. So it can be either centrally controlled or decentralized control. So with the centralized control, the bus control unit, so there is a bus control unit that coordinates the transmission, and there are different possibilities here. So there could be transmission requests from each participant or subscriber through their own alarm line, you can call it. And then the bus control unit, another one is that the bus control unit asks for their requests by using polling, or it can be a cyclical, so basically bus assignment independent of the transmission request. So you go one by one and each one gets a chance. So there are different ways, as you can see. And it could be also decentralized, so we don't have a bus control unit, but that every sender decides for itself whether the bus is available, or finds out by itself whether the bus is available or not. And there are different possibilities. As we will see also, we will continue on the next slide, but one of them is using a daisy chain, where basically there are transmission requests through a common message line. And then there is also an availability signal over a common line. And then the first subscriber that is willing to send basically grabs the availability signal. So when the bus is available, it sends a signal, and the first subscriber that needs it just grabs it and then just releases it at the end of the use, so that other can also grab this signal. Of course, this is not necessarily fair, but it's just one way of doing it. So we can also have a parallel query where every sender or every transmitter has a clear priority. So they are given priorities, and then it expresses the send request via a message line that is visible to all. And then the one that has the highest priority can send. Then we can have a cyclical bus allocation where the authorization signal, you can call it, circulates through the senders, such as creating something like a token ring in a way. And then we can have a CSMA approach, which is basically carrier sense multiple access, which we also have in Ethernet. And basically here the participant that is willing to send sends if the bus is free. This also implies that every node on the network must monitor the bus for a period of no activity before trying to send a message on that bus. So this is why it's called carrier sense. And then there are also other different new technologies currently being in use, such as optical buses, which allow unidirectional data transmission, but they also have pipelining, so it means you can have more data at the same time on the same bus. And with this we have significantly higher transmission speeds and of course improved communication options, basically by orders of magnitude. I mean, for many standard or nowadays communication, in general, the electrical transmission media or bus lines, so the standard ones, are no longer usable because they are data intensive, and the optical buses are used instead. And we mean especially the plastic fiber optic cables that are used for them. So back to the von Neumann architecture, we know that the essential task of a program is basically the change or the transformation of memory contents or data. And in the von Neumann computer, this is realized through a sequence of commands that are executed through the command cycle, as we saw it before. This fetch, decode, and execute. So now here, this way of processing basically yields something that is known as the von Neumann bottleneck. It's also known as the memory wall. And it limits the efficiency of the computer architectures, which work by moving data from memory, basically you can see here, from memory to CPU for the computation. And the way it is at the moment, these architectures cannot meet the demands of the emerging memory-intensive applications in the standard way. So in general, this von Neumann bottleneck is the idea that the computer system throughput is limited because of the relative ability of processors compared to the top rates of data transfer, because the CPU must fetch or work with the memory, fetch data from memory from time to time. So no matter how fast the CPU is, if the data transfer speed is not good enough, then the processor is idle for a certain amount of time while the memory needs to be accessed. So this is a bottleneck. And in general, the transport of a large amount of data between the CPU and the memory, which basically takes much longer than the execution of the commands on the CPU, is known as a physical von Neumann bottleneck. We also have an intellectual von Neumann bottleneck, which arises from the strong sequentialization of the commands. So the commands have to be processed in a sequential way, and this creates another bottleneck because, in general, if we can parallelize some of the things, then we can probably improve this. But according to this von Neumann architecture, this is sequential, and it's sequential down to the level of the higher language programs, and it can be slightly weakened by usual control structures, as we said. And it's known as an intellectual von Neumann bottleneck. So one way to basically reduce the impact of the von Neumann bottlenecks is through using the hardware level data types. And basically it means whatever you have in the higher programming languages, like the use of complex data structures, objects like array, list, tree, etc., that in the von Neumann computer is basically mapped into a sequence. So all of these structures in von Neumann computer are mapped into a sequence of typeless memory elements of binary content. So it can be sped up somehow. However, through doing this, we basically have a consequence, something that is known as a semantic gap between the data of the user program and the representation of this data in memory. And then we have another complexity that occurs here. Basically, we need effort for translation and administration so that we can abstract or reconstruct the corresponding data structures to the untyped, you can say, or typeless memory elements. Or an alternative is actually to support through data structures by the hardware, such that the hardware basically corresponds one-to-one to the original, to the user program data structures. And it means we have now scalar as storage elements that are, so the standard storage element contents basically are replaced by more complex and structured data units, which can be recognized at the hardware level. And With this, basically, access of a data structure corresponds essentially to accessing a memory element in a von Neumann computer. So there are different data types that could be implemented in this way, such that integers, floating point numbers, or complex numbers, vectors, matrices, or simple or doubly linked lists, queues and stacks, and files, as well as objects, could be implemented in this one-to-one correspondence to the hardware. And here we have a conceptual example of building of a data type vector at the hardware level. So on the part of the CPU will be an entire vector will be addressed through a so-called vector descriptor, which contains 3 elements. So B is the basic address or the base address of the vector, A is the number of elements in the vector, and D is the data type of the elements in the vectors. So B and A, so the base address of the vector and the number of elements, are important for the so-called address generator, for initializing of the address generator. So we know where it starts and how many elements it takes, so that it can address the individual vector components as well. And then one-time trigger by the CPU of this address generator basically initiates the transfer of a whole vector, because this is the base address, and then the number of the elements, so you can have the subsequent addresses. You can store the different elements of the vector. And in this way, the hardware support for vector operations can be simplified quite a lot. And this is a concept that is used in vector computers. And vector computers, vector calculators, or vector processors basically are CPUs that have the ability to execute a complete vector input in a single instruction. And in general, it is a complete unit of hardware resources that executes a sequential set of similar data items, like we have in vectors, in the memory using a single instruction. Another concept for basically helping or avoiding the von Neumann bottleneck is through using the cache memory, which is basically built on the concept of associative access to data. And the associative access is a special type of random access method, and this is performed through comparison of desired bit locations within a word for a specific match. And you do this for all words at the same time. So you're doing some kind of a pattern matching. So in general, in associative memory, a memory is accessed by its contents, not by the address. And we have the example here. So if you have the associative memory contain these elements here, so these are all 8-bit elements, and we compare them with the search register, and we output the results of the comparison. So here we can see this comparison happens in one clock signal, and you can also have a mask register which can point which bits to be compared. In this case, in the mask register, we can see that only the last 3 bits are important to be compared. And this is the search register, which is the word that we compare against. So here we see the first one contains 0, 1, 0, which is 0, 1, 0. These are the last 3 bits according to the mask register, and that's why the output is 1. Then the other two, 0, 1, 1, is not the same as 0, 1, 0, so the output is 0. 1, 1, 0 is also not the same, so the output is 0. And you can see the last ones. This one is the same, 0, 1, 0, so we have an output 1. This one is not the same, and this one is again the same, so we have 0 and 1. So we have the result of the output. If the comparison was not successful, then the corresponding bit position in the comparison indicator is assigned with 0 or 1. Basically, if it was not successful, you get 0. If it was successful, you get 1. So typical use of this associative memory is for searches. So if you need to search for a specific number in a sequence of numbers, then you can use that. And of course, there are also disadvantages of using this memory, which is that we need complex hardware that contains some kind of comparison logics built in. And we also have associative processors that implement this, that can basically execute the operations in an associative memory, such as the CARPA one, which CARPA stands for Content Addressable Processor Array, which has been published, done in 1991. And as you can imagine, the problem here is that it is difficult to program, and it has only specific applications. So neural networks could be understood as a kind of associative computer structures. And in general, the common use of this associative access, as I already noted in the previous slide, is in cache memory. So another way to basically resolve or relieve the von Neumann bottleneck is also through the use of parallel processing. And parallel processing is basically a computing technique when you have multiple streams of calculations or data processing tasks that happen at the same time through numerous central processing units or CPUs. So this is basically frequently found in modern computers, as we will see. In general, it can be done at different levels. And because of the concurrent or processing that happens at the same time, certain resources are required more than once. And parallel processing, based on the level at which it happens, it can be divided into 3 classes. So you can have certain parts of the processors being available in more than one instances. And you can have like several arithmetic logic units, for example. And there are some typical instances or typical representatives of this are the pipeline computers or the vector computers or calculators that we mentioned before in our previous slides. Then you can have this at the level of the processor. So you can have full processors available in more than one instances, and they have then very fast or high-speed interconnection network. And this is what we see often in the modern multi-core processors. So this is nowadays very common. And then we have the third level, or the third class, where you have more than one computers that are actually loosely connected to each other. And this is also very common today. I mean, we also have the term of distributed systems, which refers to this connectivity or connection of computers. So we can have workstation clusters or client-server systems, or we have heard already about grid computing, or now we also talk about cloud computing. So this is all about, these are all different kinds of distributed systems which connect more computers in parallel. So one of the most popular taxonomies for computer architectures has been proposed by Flynn in 1972. Actually, there are some conflicting years here also. You will see it as 1968 as well. So this classification scheme or taxonomy is basically based on the notion of streams of information. So here we talk based on the streams. So we have two types of information flow into a processor, and one is the instructions. So this is the instruction streams, which the instruction stream which defines the number of control units. And then we have the data stream, which defines the number of memory units. So the instruction stream is defined basically as the sequence of instructions that needs to be processed by or performed by the processing unit. And then the data stream is the data traffic that needs to be exchanged between the memory and the processor. So according to Flynn's classification, we have 4 different basic combinations of computer architectures. So the first and the most simple one, that is also based on the von Neumann architecture, is the single instruction, single data. So here you can see this is like a matrix. Here we have the different instruction streams. So you can either have a single instruction or multiple instruction, or you can have single data or multiple data. And the simplest one, as I said, is the single instruction, single data stream, which means we have one sequential incoming data stream and one single processing unit to execute this data stream. And this is like, usually you find it in, this is one of the oldest, and even today you find it often, most common type of computer. But nowadays, as I said, modern computers are more multi-core and they implement different architectures. And now this can be found only in older computers or some older mainframe computers. So then we have the next type is as you can see here, we go in this single instruction, multiple data. And here we have basically one instruction operates on many data. So here you have many processors, but you see we have one control unit. So we have a single instruction, and usually this is like these multiprocessor systems that have parallel computing architectures. And an example for this would be I mean, this is also very popular architecture for graphical processing units, so GPUs. And what they can do is, like, you can have a single SIMD instruction to add, for example, a given number to 64 numbers. And this can be achieved by sending 64 data streams to 64 arithmetic logic units, which then form 64 sums within a single clock cycle. So all is done in parallel. And why this is useful also for graphical processing units, you can imagine when you have games, for example, very often you have operations that need something like this, when you just transpose images or move characters in an animated movies or cartoons or which are part of the games, for example. And then this just needs to add a given number to a bunch of other numbers. And this can be then achieved in parallel. In addition to this, we also have, we can have multiple instructions and single data. But just so you know, I mean, this kind of machine in practice, there is no viable machine basically that implements this architecture, but still it's theoretically part of this architecture. So in multiple instruction, we have basically a number of processing units that perform different operations by executing different instructions on the same data set. So here we have the same data, but we have different instructions. And finally, we have the last one, multiple instruction, multiple data, where each processor in a multiprocessor system can execute different sets of instructions independently on the different set of data set in parallel. So this is basically opposite of the single data, single instruction multiple data, in which single operation is executed on multiple data sets. So nowadays, parallel computers are either single instruction multiple data or multiple instruction multiple data. And besides that, we also have two different architectures, which we are not going to go into depth. We can have also something which is known as single program multiple data architecture, where all processors must go through the same program, but there are different program control flows. And then we have the symmetric multiprocessor, which is basically multiple instruction, multiple data with shared memory, which is today it's the common server architecture. And here all processors have basically equal rights. So parallel processing can basically happen at different levels. And there is one finer division of this into 5 different levels of parallel processing. And we also have a more coarse division into fine-grained parallelization and coarse-grained parallelization. But in general, we can have parallelization at instruction phase. You know, we already discussed that we have the fetch, decode, and execute, the different phases of how instructions are being processed. And you can already have there some level of parallelization or pipelining. So basically, without this instruction level parallelism, the processor can only issue less than one instruction per clock cycle. But as we can see also on our next slides, this improves the performance of the processors. Then we can also have at the level of basic operations, so how addition, subtraction, multiplication, etc. is being performed. Then we can have it at the level of statements in relation to a programming language. For example, this is very common in loops. So some loop-independent operations can be vectorized, such that you have a pipelined execution, or or loop step execution, basically, of single instruction, multiple data machines. Then we can have it at the process level. Already in some programming languages, this is a very common concept. So threading, like in Java, we have the thread concept, or simultaneous multi-threading, where basically a summary of a sequence of instruction forms this functional unit that is known as a process. And it also has its dedicated address space. And then different processes can be then run at the same time. These are usually known as lightweight processes, because then we have another formation which is known as a job. So then this is basically a self-contained user program that consists of more processes. So it is a bit heavier than at the process level. And then you can parallelize different, or process in parallel different jobs. So all of these are different levels at which you can achieve parallel processing. And there is also, as I already mentioned, it can be also defined into fine-grained parallelization. This means you go up to the statement level. So this is all known. The first three levels are basically known as fine-grained parallelization. And then the last two, so the process and the job levels, are known as coarse-grained parallelization. They all have, of course, different challenges associated with them. So another way to improve the performance of the CPU is basically through pipelining. And pipelining is basically the process where you arrange hardware elements of the CPU so that they can allow for simultaneous execution of more than one instruction. In general, we have a linear arrangement of a number of processing units, which can be specialized as well. And we use BE for denoting of these processing units. So you can call them processing units, or processor parts, or just processors. And what is very important is that you have a possibility to split the tasks into a number of, if possibly, equally sized partial tasks, which can be executed sequentially, so one after another. Then what do we do is every processing unit performs one part of this equally sized, possibly partial task. So it performs one partial task, and then it hands the result to the next processing unit or processor. And you can see here, so then the work rhythm is basically always controlled from a global clock, and the input and the output of the processing units also follows this global clock or cycle. So what happens here, we have a temporal overlap. So as soon as one task So here we have the first task and it has been completed. As soon as it has reached the processor 2 or processing unit 2, so it has completed. So the processor 1 is basically idle or free, so it can start processing the second task. So if this is the clock cycle, this is how they get executed. So you can see that as soon as this one is free, it starts working on the second task, and then on the third task, etc. So the idle time is basically greatly reduced, and with this we achieve a much better efficiency of the whole system in general. So here we see an example of pipelining where the task command processing is divided into 4 subtasks. So we said that was the basic requirement, that we can divide or split the main task into 4 partial tasks or subtasks. And here we have divided it into 4, and one is fetch. You fetch the command or the instruction. Then it's decoding of the instruction. Then we need to fetch the operand, and then we execute. And both O and E, so these 2 last, basically usually correspond to the whole execute phase as we learned before, but here it is split into 2 subtasks to make it easier. So now we have 4 processing units, you can think, and each processing unit is responsible for one of these 4 subtasks. So what happens at the first clock signal, you see we start processing the first command or the first partial subtask, which is fetch the instruction. So once we have fetched the instruction, it goes to get decoded, but this another processing unit is responsible for it. So this first processing unit becomes available. So at the next clock signal, we have the first processing unit starts to basically fetch the second instruction because it is free, and this one is being decoded. So in the next clock cycle, it goes basically you can see that once it has been decoded, it can fetch the operand. So it leaves this the decoding base processing unit free and moves to the next one. So this one can start actually decoding the second instruction, etc. So you can see this is basically the concept of pipelining. So if we performed all of this sequentially, we would have needed 16 clock cycles. But because now we have pipelined, we only need 7. So as you can see, this is a very simple example that illustrates the efficiency that can be achieved using pipelining. You can imagine how this would scale when we have real life operations, real world operations, and real world instructions. So as further remarks, we can say that we can differentiate pipelines based on the level of their application or based on the changeability of their function. So as we saw on our previous slide, we saw what is known as an instruction level parallelism, where we basically perform parallelism based on the phases of the instruction. So fetch, decode, etc. And then it can also happen at the level of elementary operations, which is known as arithmetic pipelining. So in which case we divide these arithmetic operations in different partial tasks or subtasks, and then the processing units are specialized, as we mentioned before. They can be specialized, and then we talk about adders, shifters, etc. Or pipelines can be differentiated based on the changeability of their functions. So it can be single function pipeline, where it's always the same sequence of operations that is executed, like we saw in the previous example. Or, like we have in the arithmetic pipelining, we can have different operation sequences taking place. So different operations and different sequences as well. So in general, all the modern computers and microprocessors use pipelining, as you would imagine, and it is especially used in vector computers and in signal processors. So modern processors in general can have up to 30-stage pipelines, well, even higher nowadays, because this is a little bit dated information, and this can lead to problems with emptying of the pipeline because of dependencies that that appear due to the consecutive activities. And this is why one of the main techniques that is already built in modern processors is something which is known as speculative program execution, which means they execute speculatively possible consecutive instructions. So they guess what could be the next instruction, and with this they also have a speculative result, and then afterwards it is corrected if this estimation was wrong. So they are kind of one step ahead, so to say, at least. So with this, time can be saved, and as I already noted, it has become a standard technology in modern computer architectures. So in general, the possibility of saving time using pipeline is one of the main arguments for hardware implementation of these algorithms, where you will hear more in your lecture on efficient algorithms. And here we don't go that much in detail of this. So in general, CPU works at a single time only on one task, which means processors can normally process only commands from one thread in each cycle. However, these threads do not use the whole computing power of the processor. For example, if you have only integer operations and no floating point operations, then you don't use the whole capability. And the estimate is that only 35% of the theoretical computing power of a processor is actually being used. From what we know already and from what we've seen in the previous slides, most of the processors that we have nowadays are multi-core. So they basically contain several processing units that can handle different tasks at once. And this is a common concept. However, there is another concept, which is something that is known as processors with simultaneous multi-threading, or Intel uses the term hyper-threading, which basically has several sets of registers on one processor chip, and therefore it can work, or it can divide the work into two threads at the same time. So what it means is that the CPU divides up the physical core into virtual cores. In this case, two virtual cores that are treated as if they are actually physical cores of the operating system. And these virtual cores are what we call threads. So then the computing power is not basically increased, it's just better utilized, you can say. So, of course, you can imagine that this has certain cost because you need to facilitate this. So what it costs is only 5% more gates and a slightly higher power consumption. But the benefits of this are something that makes the difference, which means in the best case we can have a double performance. And if basically these parallel threads are complementary, so we can increase by double the performance or duplicate basically the performance of the processor. And in the worst case, it can lead to slowing down because of the overhead. So, for example, if you have parallel threads that want to use the full cache at the same time. And in average case, we get something in the range of 10 to 20% performance increase. Multiprocessor systems or parallel systems, they are increasing in importance nowadays. They are becoming very common. And these are systems that have multiple processors that work in parallel, that share the computer clock, the memory, bus, peripheral devices, etc. So these are nowadays basically many complete processors which follow the multiple instruction, multiple data principles, but also often as a single program, multiple data. And the main application is to provide parallel processing at the task and job levels. So basically in what is known as a coarse-grained parallelism. There are different ways how we can differentiate between these different multiprocessor systems. One is based on the type of processors. So if all processors are same in hardware, then we talk about homogeneous systems. Otherwise, we talk about inhomogeneous or heterogeneous systems. Then it could be differentiated based on the type of the processors. So if all, or the functionality. So if all processors have the same functionality, then we talk about a symmetrical system. And then when we talk about a parallel or multiprocessor system, we talk about symmetric multiprocessor. So this is basically today's, as we mentioned before, it's today's server architecture. Otherwise, if they do not follow, then we talk about asymmetrical systems. Then it can be differentiated based on the coupling of the processors. So they can be either strongly coupled or they can be weakly coupled. So basically, if they have access to a shared or a common main memory, which is known as a shared memory, and it's especially available with symmetric multiprocessors, then we talk about strongly coupled. But if the communication is through exchange of messages, so like message passing, or they have distributed memory, then we talk about weakly coupled processors. However, today's parallel computers usually have distributed shared memory, or basically a virtual shared memory. That means that the advantages of the shared memory are realized through simulation of the systems with distributed memory. And here we have some examples of some machines, multiprocessor systems that have been beasts basically at their time, but we are not going to go into detail because this development has went on. I mean, you can only see some of the descriptions, but so UltraSpark Sun or Macintosh G5, it was a beast basically at its time. So it featured more processors in one workstation with shared memory, and it was a strongly coupled system. Then we can see a description of a workstation cluster, which is a couple of hundred of personal computers which could run Linux or Beowulf, which were basically through messages connected, coupled through messages, and they also had a shared memory, etc. So you are free to look at the descriptions of the other at home. But this has went on, so nowadays we have many machines that have different and new and build and basically implement even newer technologies of this. And as we saw, the parallelization is often achieved through exchange of messages between the computers. And this, as we saw, it was the way it was done in UltraSpark or the multiprocessor Max. And this is achieved through mainly two different ways. One is either through special programming languages that enable this. So there is a HP Fortran or the Java with the special APIs, so which allows socket programming or remote message invocation. These are the APIs. And then we also have a standard function libraries, which can be used in different programming languages. And the most popular ones are the Parallel Virtual Machine library and the Message Passing Interface library, which is available for Python or Java, etc. And this will be basically a bigger part of this would be a bigger part of a lecture that is focused on distributed algorithms.